Before we get into this, I want you to kind of see that this is going to be a long video, and as you can see, we've got a lot going on here. So what I encourage you to do is take your time, take it slow, pause, and think about how we're modeling and going through each of these problems. Because systems of equation problems can be overwhelming at first, but once you get the hang of the patterns that arise and the way to analyze the questions, they do become much simpler, and they can even be a puzzle that has some slight enjoyance in solving. At least it could be less miserable than it has in the past. Now what we're going to do is we're going to take a look at a few different word problems and how we can apply our understanding of word problems and our understanding of systems of equations in order to evaluate these. Sometimes equations are given to us, and sometimes we have to write our own. So we'll need to read through these to kind of see some structures that will occur. Just like with before, we want to understand and choose a variable. So look at what are we trying to solve? What is the question asking for us? And then define the variable that we are going to use in order to solve. The thing that we want to solve for is going to be our variables. Since in these examples we're dealing with systems of equations and two variable, that means we're going to have two variables and two unknowns that we'll be solving. We'll also have two equations that are modeling two different parts of our scenario. If we need to write an equation, we can translate a sentence describing our scenario into an algebraic equation, and then we can solve and interpret our solution. We can use whatever method for solving a system of equations that we choose, and so we may want to analyze the structure of the system to see what method might be the most efficient. So go ahead and take a second to read the problem here. Pause if you need more time. But what we're basically looking at is two functions modeling the sale of fresh fruit versus processed fruit. And we have our variables where y represents the amount of fruit. Y equals the amount of fruit. And in one equation it represents the amount of fresh fruit, while the other equation represents the amount of processed fruit. And x represents the number of years after 2006. And so we've got our variables, and so what we want to find is what year will the amount of fruit be equal. So we're looking for the value of x when the y's are equal. Well, if we want to find what value of x makes both y's equal, and we have our two equations here, well, this becomes just a substitution problem within our system. Find out what value of x makes y's the same. And we could use elimination, but since both of these equations are already in slope-intercept form, then we can go ahead and substitute one equation into the other, since we already know that y equals each of these expressions. So we just go ahead and set both sides equal to each other. So we have our fresh fruit. When will the amount of fresh fruit equal the amount of processed fruit? And so we can go ahead and solve the system using our properties of equality, which I'll go ahead and do now. Now x is going to be a long decimal value, so I'm going to go ahead and just round it to a couple decimal places. So the value of x is approximately 3.53. And so we want to go ahead and interpret this answer. And we want to say, okay, well, what we're looking for is identifying that approximately 3.5 years after 2006, the amount of fresh and processed fruit, were equal. That's, remember, because X is the amount of years after 2006, and we're looking at Y being the amount of processed and fresh fruit, and those amounts should be equal. And so 3.5 years after the year 2006, well, if we take our 2006 and we add 3.5, we get the year 2009.5. So it was in the year 2009. And we could say, well, it was approximately in June of 2009 when these amounts of fruit were equal. Now for the second example, we are not given equations. We have to write our own. So take a minute to read the problem and think about what we need to solve for and what our variables will represent. Pause if you need more time. But what we're looking at is finding two numbers. And so our variables, we can use X and Y, will represent, X will represent the first number, while Y can represent the second number. And so we can go ahead and parse through each of these sentences to identify our equation. So we'll start with the first sentence. A first number, well, we know our first number is represented by an X, is, that's our equal, 4 less than a second number. So we need to subtract 4 from our second number, which is Y. So to simplify this equation, we can write it as X equals Y minus 4. Then for our second sentence, we have 4 times the first number, so that is 4 times X, is equals 6 more than, that's add 6 to twice the second number, 2 times Y. So we can simplify this equation as 4x equals 2y plus 6. Now take a look at the structure and think to yourself, what is the best method or most efficient method that we could use to solve this system? Well, since one of our variables is already isolated, substitution makes the most sense. So we can go ahead and substitute in for x. And we'll go ahead and solve. So what we've done is we've found the second number. We know the second number is 11. And then what we can do is use one of our other equations in order to find the first number. Well, our first equation tells us the first number in terms of y, our second number, pretty easily. X equals 11 minus 4. Therefore, our first number is 7. So our numbers are 7 and 11. Next problem here. Go ahead and take a minute to read through it. And again, think about what it is you're solving for and what each variable is going to represent. Feel free to pause if you need more time. So here what we have is 2 cars leaving Kansas City. And we're trying to find the speed of each car. So we'll start by identifying that x can be the speed of the first car, and y can be the speed of the second car. Let's draw a little picture to kind of get a visual for what's happening here. So we have Kansas City on a map, and two cars are leaving. One car heads in one direction, and another car heads in the other direction. And so we've got these two cars going in two separate directions. Now, after some time, these cars have traveled a combined distance of 297 miles per hour. Or I'm sorry, not miles per hour, 297 miles over those 3 hours. So they've traveled for the same amount of time, but because one car is traveling faster, then we know that one car has gone further. And so we can't just split the distance in half because one's gone more distance in that time due to its higher speed. So when we're given a problem like this, we need to consider our distance formula. Recall that our distance formula, distance equals rate, also known as speed, multiplied by time. And since each car is traveling a different distance, then each car will have a different expression representing its distance. They'll have a different expression representing their rate, but their time will be the same. And so let's think of a couple ways that we can model this. Let's think about the distance aspect first. So in some basic terms, the distance of car 1 plus the distance of car 2, has to equal their total combined distance. I'll just label that as total distance. Well, we know the total distance is 297, but how do we represent the distance of car 1 and car 2 in a way that allows us to use our variables x and y? So keep in mind that our distance is not x. Our variable x represents the speed of the car. Well, using the speed of the car with our variable, how can we go ahead and model the distance for car 1? Well, let's look at a little chart we can make for car 1 and car 2. And we've got some aspects to get our formula. The rate of the car times or multiplied by the time the car travels will equal the distance that the car travels. And so if we want distance, this column here, so that we can fill out the rest of this equation, well, we need something that represents it in terms of our variables. Well, let's think back. Our variable x represents the speed of the first car. So that's the first car's rate, and the second car's rate is y. And then time, well, time is the same for both of those. They were both traveling for 3 hours. And then lastly, we can go ahead and actually get something that represents our distance as being 3x and 3y. So now we have expressions in terms of the variables that we defined that model the total distance of the cars traveling. 3x plus 3y has to equal 297. So there's our first equation. Now the second equation, let's think about what else is being told us about the cars and their speeds. Because again, our variables represent the car's speed. Well, what we've been told is that one car is traveling 5 miles per hour faster than the other. So one car, let's say the first car, car 1, is 5 miles per hour faster than car 2. Well, the speed of car 1 is x equals 5 miles per hour faster. We're adding 5 to car 2. So the speed of car 2 is y, and we are adding 5 to that. So now we have our second equation, x equals y plus 5. So we're given a system. I encourage you to go ahead now and think about, with our system, we can solve for x and y, we can find the speeds of the cars. What is going to be probably the most efficient way to solve this system? And I encourage you to pause now and try to work it out on your own. That way you have plenty of time, and then check it to my solution when you're done. Now your process might be slightly different than mine, but as long as your arithmetic is valid and you end up with the same result, then there's no problem. I'm going to go ahead and use the substitution method since a variable is already isolated, and I'm going to substitute y plus 5 into x of the other equation. So we find the speed of the second car is 47, and then we can substitute it back into one of our two equations. I'm going to use the shorter one for y in order to solve for the speed of the first car. Therefore, the first car has a speed of 52. So the speeds are 52 miles per hour and 47 miles per hour. Now we're looking at a mixture type problem. Go ahead and pause and take a minute to read about it and think about what our variables would represent. Here we have a mixture problem, and after this I'll throw in a bonus one with another type of mixture problem that you might see. But here we have a pharmacist needs 70 liters of an alcohol solution, and she only has different percentages that she could mix together to get a 50%. And she can't just do half and half of each. That's not how percentages work with our mixtures, so we need to be very specific about the quantities of each one. And so we want to figure out how many liters of each solution she should use in order to get her desired solution of 70 liters. And so right there, that tells us what our variables need to be. X can be one of the solutions. We could say X can be the number of liters of the 30% solution, and Y will represent the number of liters of the 80% solution. So we're going to be getting a volume. X and Y both represent different volumes. And so let's think about what happens. Well, when we mix stuff together, we're taking the volume of our first solution, X, and the volume of our second solution, Y, and getting a total volume of our mixture. So for example, if we mix together 5 liters of solution X and we mixed 7 liters of solution Y, well, we would end up with a total volume of 12 liters. And so that's just a simple addition of however many liters of X plus however many liters of Y. We need to end up with 70 liters total. That's our total volume. So there's our first equation. Pretty straightforward. Now for our second equation, it's a little bit more complex, but not much, and you'll often see this type of problem, and it's a very, very formulaic idea, and you can use this thought process over and over. Even on some type of SAT questions, you'll see mixture problems. So the pharmacist needs 70 liters of a 50% alcohol solution. Well, this means that only 35 liters of that solution is actually alcohol. And so what we're looking at is the amount of alcohol. in the solution. The amount of alcohol in the solution, and for our equation, we're looking at the total amount of alcohol. Well, to find the total amount of alcohol, that was 35 liters, I just multiplied 70 by 50%. So to figure out how much alcohol is in each other mixture, the 30% solution and the 80% solution, we do something very similar. We look at, okay, well, the volume of X is only 30% alcohol. So the value for our first term is that we're going to take the volume of the X solution, and we're also going to multiply it by 30% to figure out the amount of alcohol in the X solution. So we're looking at the amount of alcohol in the X solution. And by comparison, we're also looking at the amount of alcohol in the Y solution. So Y times 80%. So if we had 10 liters of our X solution, well, only 3 liters of that would be alcohol. And if we had 10 liters of our Y solution, 8 of that would be alcohol. And so we need to add those together in order to get the appropriate amount of alcohol in the final solution, making sure that we have exactly 70 liters and that 35 of those liters are alcohol. So we can simplify this. Remember, we can't use percents and percent notation. We need to write them in decimal form. So we can rewrite this as 0.3x plus 0.8y equals 0.57. And we know that 0.57 actually equals 35 liters. So we have our second system. Now, again, pause and think about what's the best way to solve it. And then go ahead and apply your method. Pause if you need more time. By looking at the structure here, I visualize that this method would be much easier to solve by using elimination. Since both of the equations are in standard form, I can also look and see, well, whichever variable I want to eliminate, either x or y, I can multiply our first equation up here by the opposite of one of those coefficients, such as negative 0.3. So that ends up giving me negative 0.3x minus 0.3y equals negative 21. And now that I have that, I can go ahead and add these equations together. The x terms will cancel. I will have 0.5y equals 14. Therefore, y is 28. So the number of liters for the 80% solution is 28 liters. And then we can go back to one of our original equations to solve it. X plus 28 equals 70. So x has to be 42. So we have 42 liters of the 30% solution for our mixture. Now, I told you I'd have a bonus question for you, and so let's go ahead and take a look at that now. Here we have another type of mixture problem, which uses dollar amounts rather than percentages, but the overall concept is still going to be the same. We're mixing two things, chocolate and nuts. So take a minute to read through this problem and see if you can't use the similar structure that we used before in order to write your own equations and then solve. Pause if you need time. So generally speaking, what we're looking at in a much broader sense is that we are mixing chocolate and nuts. And so we can use those as our variables, or you can use x and y. And so when we're mixing stuff together, just like with before, however the much weight of chocolate that we have, plus the amount of weight in nuts that we have, has to equal the total weight that we're trying to get. Well, we don't know how much chocolate we have. That's what we have to solve for, is the chocolate weight, how many pounds, and the nuts weight, how many pounds. And so we're just looking at a simple addition, just like before, to equal the 30-pound total that we need. Now, the other thing that we have to look at and consider is how much they cost. And so they want to make sure that it costs a certain amount for the total weight. And so the chocolate sells for $4 a pound. So just like with the percentages, we're going to be multiplying chocolate by the number of pounds, and by the cost per pound, and as well with the nuts, $2.50 per pound, and that has to equal a cost of $3.50 per pound of the total mixture, which in this case is 30. And so now what we've done is we've got our system of equations set up using a very similar model to our percentage mixture, and we can go ahead and take the time to solve. So go ahead and solve now for both of those. So here I chose to use the elimination method again, multiplying the first equation by -4 so that my variable c eliminates, leaving me with -1.5n equals -15, so n equals 10. So that means we have to have 10 pounds of nuts for the mixture. And then if we substitute 10 and we have to have a total of 30 pounds, that leaves 20 pounds of chocolate. Now let's go ahead and finish the last problem from our notes. Go ahead and take a few minutes to read the question and see if you can't identify what is being asked for. Feel free to pause if you need more time. So what we're trying to solve for is the break-even point. And I want you to recall from earlier in the chapter, we talked about a break-even point. Break-even is when the cost that it takes to manufacture something is equal to the revenue that is earned by selling a good or a service. And so what we have to do is write two equations that model cost and revenue. And so let's start with cost. Well, cost will have to equal any startup costs or initial investments plus the cost of manufacturing each item. Each item has a certain cost associated with it. The more items you make, the more that cost goes up. And so when we look at this problem here, we see that the company purchased $3,000 of new equipment, so that's a cost to them. And then as they go ahead and manufacture these items, it costs them $3 per item. And so the total cost for them to manufacture these goods is $3,000 plus 3 times however many items they make. Now let's take a look at revenue. Revenue is just the amount of money they make by selling it. We're not talking about profit. That's different. We're looking at the amount of money they earn. And so here it's a much simpler formula where the revenue will equal the $5.50 for every single item they sell. So the break-even point tells us the cost has to equal revenue. And so very similar to our original equation, we need to set cost equal to revenue. So cost goes in this side and revenue goes on this side. So we need to solve for 3,000 plus 3x equals 5.5x. And so that was a substitution. We're going to go ahead and solve. So here we have that they need to sell 1,200 packages in order for them to break even. Now something else to be aware of that's not given in this problem, but it's good to know, is the concept of profit. And profit is what we get when we take revenue and we subtract cost. And so given these cost and revenue functions, we can actually write a new equation by combining these two. So profit will equal our revenue function minus our cost function. And we can simplify this equation. We can distribute. And then we can go ahead and combine like terms. And so here we actually have an equation that models profit. So we can look and see, well, if they sold 1,200 items, how much profit do they make? And since it's a break-even point, it should be 0. So we'll take y equals 2.5 times 1,200 minus 3,000. Well, that does indeed give us 0. So we see that this is our break-even point. They've made no profit, but they also haven't lost any money. If X was a value less than 1,200, then they would have negative profit, meaning they haven't made enough money to break even on the cost associated with the project. But once they sell more than 1,200 units, then they're starting to actually make money on every single item that they sell.